So the announcement is that first you go to your web work and make sure that you log in with your Berkeley email account and you write your full names instead of just any random names. And another thing is like for Zoom meeting, you also need to like log in with your Berkeley email and full name. Yeah, question. I always access web work from B course. Where should we log in? Like how participant could ask us to do? Like I have never do the web work thing before. So can anyone like who knows how to do that answer the question? Okay. So I guess I will confirm with professor on like if you are doing that if you got your practice exam and like if you do that for your practice exam are you good or not? So I guess I will confirm with her about that. Yeah. So but like I think in chat like you are saying that it should be fine if you are doing the web work thing. Yeah. So I think the reason like according to what the conversation we had in the chat, the reason why professor come here to each section to ask is because some of the students who never do the web work homework, so they don't have like a very good knowledge about how to do that. So as long as you are doing that, you should be fine. Yes. So and I also like if you have any question on this web work logistics, please send me an email because I don't know anything about like how do you log in and do the web work problems. I just graded. So like if you have any like logistic problem like that, just send me an email. So at the end of the day, I will compile a question like for like several types of problems, logistic problems, and I will either ask my fellow JSS or ask professor on like your specific logistics. So again, like send me emails if you are unknown about how to do the web work logistic. Okay, so the third announcement is so your grade for quiz 10 is up. So definitely check your grade. And also like some of students lose 1 point for not labeling problems to pages. Like for those who didn't lose this 1 point, that means like you're doing exactly what I want. For those who actually lose 1 point, the way you can get this 1 point back is to tell me that you know how to do that. And I'm just gonna share with you how exactly do we do that. Right now, can you see my like browser? Like for those who like for everyone, like can you see my browser? Yeah. So the way you do that is you go to Gradescope and maybe like I don't know, I just click on one of my course. And if you want to like do a summation, like for example, this is the quiz summation, and you do a submit PDF, and you select a file. Maybe let's select maybe not the quiz, maybe something like that. Like just a random file. Like, and if we want to submit it, we upload the PDF. And then on the left-hand side, for this assignment, specifically on my other course, it doesn't like give you any problems, but like it's supposed to have like true and false, problem 1 and problem 2 here. So what you need to do is like, for example, you have like true and false in the first 2 pages. So you click this and click the first 2 pages. So you successfully assign true and false problem into the 2 pages. And say like if you have like problem 1 and you want to assign problem 1 into the 3rd pages, and you just like assign problem 1 into the 3rd pages. But like there will be like a lot of tabs here for my quiz submission. So just to do that, to assign questions 2 pages. And let me know in the chat if you have any problem on doing that. And also like you should be able to see the quiz 10 right now. So let me go back to my iPad. If you have everything in one page, that means you're just like, you just click on the left hand side, do the labeling, and match all the problems. So like on the left hand side, you will have true and false, problem 1 and problem 2. And if you write it on just one page, so for example, this is your true and false, this is problem 1, this is problem 2, you first click true and false and click this page. And then you click problem 1 and then click this page again. And then you click problem 2 and then click this page again. So this is not a one-to-one bijection function. You can like assign one value, like you can assign multiple values into one page. Yes. So I mean, I do mean quiz. Oh yes, your grade for quiz 9 is up, and you should be able to view. You should be able to submit quiz 10 right now, like which is what we will do like shortly. Yes. So like yeah. So for those who do want to get this 1 point back, just send me or actually send a regrade request on this -1 point. I believe I'm -1 in the true and false section, so you can like send me a regrade request on this, and then I will add your point back. And again, like from now on, like you should know how to like do the labeling thing. Like whenever you didn't do the labeling, I will give you -1 point. Yes. So so for the quiz collection, we don't have quiz collection for quiz 9, because Aaron did pretty well. I think you are like, you know the knowledge for quiz 9. And I mean quiz 8, submission deadline has already ended. So we'll just say like how you do on quiz 10. And I actually make quiz 10 pretty easy, so you guys should be able to receive a pretty good grade on quiz 10. So I mean, I only do quiz collection on when everyone's doing not so good. And for and we'll see how it works for quiz 10. And one good thing. Okay, so there's like a lot of questions right now. So first of all, quiz, the maximum of quiz is 12, but originally the lowest point, like the range for your getting grade is -2 to 12. Because like if you didn't do anything in problem 1, problem 2, written problems, and you mess up with, you did wrong on all true and false, you will get -2 instead of 0. So but Gradescope doesn't allow negative scores. So right now I just like shifting the distribution into 0 to 14. And we know that for a distribution, if we shift it everything by 2, it doesn't change the distribution shape. So I just basically make the range from 0 to 14. So if you receive a 14, that means you are receiving a 12. If you receive a 9, that means you are actually getting a 7. So, oh yeah, statistic. So the mean is around 8. Oh, I mean like around 10. Like mean and median is all around 10. So, but 10 stands for 8. So 10 out of 14 is 8 out of 12. Yes, so that's the statistic. Yeah, I mean, like if you actually do the quiz question for quiz 8 and you forgot to submit, if you don't know that, like you can submit to me by email. I mean, theoretically it is after the deadline, but I don't really care. Like as long as you are like you are doing the quiz question and you know how to solve this problem. Like all I want for you is to understand this problem and know how to do it if I give you another problem. So I don't really care about like the deadline. But don't treat my like merciness as something like for granted. So you will like submit everything late. I mean like just like I allow you to do that, but like it's better if you can do that as soon as possible. So that's all the announcement. So let me quickly review the concepts that we covered in previous lectures. Yeah, and I believe there's no latency problem. If you have one, may ask. I will answer the question later. So on last Friday, we went through Chebyshev on Chebyshev's inequality. So what is Chebyshev inequality? It is defined that so if x is a random variable and it has a distribution, so we know that if we are given a distribution, we know x has a if x is a random variable, we know that it has a mean and it also has a standard deviation, and we're basically bounding the area for any distribution. So that's like, so for probability of mu minus k sigma, where k is a constant, less than x, less than mu plus k sigma, we want to bound this range. And Chebyshev says that this is strictly greater or equal to 1 minus 1 over k squared. But like if you look at this Chebyshev inequality, it works for all k, but like it is only useful for k is greater than 1, because like when k is greater than 0 and when k, like let's say useful on the range of k greater than 1, because when k is greater than 0 and less than 1, 1 over so what I'm talking about, so that means 1 over k squared is a very large number. So that means 1 over k squared is greater than 1. And so you're essentially talking about a probability that is greater than 1 minus a number that is larger than 1. So you're talking about this is greater than a negative number. But we know the probability is always a positive. It's always a non-negative number. It actually ranges from 0 to 1. So it doesn't give us any useful thing for Chebyshev inequality. So it is only useful when k is greater than 1. And some variation, some variation of Chebyshev is that so previously we were talking about the distribution in the middle. So another thing I was mentioning is that it is easier to know the graph instead of like plainly understand the algebra equation. So what that Chebyshev equation means is like if you have a mean here and you have a mean minus k sigma and you have a mean plus k sigma, essentially you are funding this area. You're saying that this area is at least 1 minus 1 over k squared. But like if we have this inequality, that means for the same distribution, you can also give an upper bound on the tails that is not in the middle. So essentially one variation of that is that when we are talking about x greater than mu plus k sigma and x is less than mu minus k sigma, that's like these two tails here. So we can also like write it as the probability of x minus mu greater or equal to k sigma. So we know that this is just like the complement of the ordinal equation. We have like upper bound in the middle. So we are talking about the middle part is at least 1 minus 1 over k squared. That means the bond is at most 1 over k squared. In fact, I think this is this used a lot than the actual definition of Chebyshev. And another variation is probability of x minus mu greater than r is less than the variance of x divided by r squared. That's like directly we get from this equation here. So it's basically we define r to be k sigma. So 1 over k squared on the right hand side will be k. So k is r divided by sigma. So it's sigma r squared. Maybe did I mess it up? So yeah, because we're talking about 1 over k squared. So that's actually sigma over r squared. So which is r squared over sigma squared. I mean, we know that sigma squared is just the variance of x. So this is like a easier format of the previous solution because we don't need to like actually think about what are the k sigma. We can just like use any r, and then at last we will like write it the variance outside. So there are some variation of Chebyshev. And on Monday we went through some of the basic statistics and sampling. So something you need to know in your mind is that this integral is always equal to 1. So that's like the PDF for normal distribution. So if you do a negative infinity to positive infinity, the area underneath that should be 1. So that's something you should know in your mind. We actually prove that using multivariable calculus. But like, I mean, see if you guys are interested. If you guys are interested, I will prove that in the discussion after the quiz. If you guys are not interested, I will just not prove that. And then we also talk about, and essentially, there's a lot of concepts, but essentially for doing the problem, you just need to find this course and check the normal table, which we will do a lot of this type of problem in the discussion later. So with that being said, you have like a minute to ask the last minute problem. If not, I will just upload the quiz right now. Okay, it's up on the B course under the folder file. See if you can find that. You see it? Maybe like refresh your browser. Okay, great. So you have up until 10:26 to finish the problem. I mean to upload on the Griscope, not just finish. So let me change the deadline to 10:26. Yes, you can use a standard normal table. The quiz end at 10:26. I mean, you have to like submit on Gradescope and assign problems to pages before 10:26. You only have 1 minute to submit your quiz, so be sure to um, do the submission right now. Okay. I think by this time,
Wondering how you can help? Click the link below.
is that anyone playing some video or something? Like, if you're not like saying something, please mute yourself so that it doesn't influence others. Okay. So, okay. Okay. So everyone by this time should already submit your quiz. So let's work on the problem set. Or actually, are you guys interested in like how do you solve this integral? Like, so let me know if you are interested. If there's not too much people interested, I'll probably just not talk about that. Okay. Okay, seems like not too many people are interested in how to solve this integral. I guess we will just not talk about that. But, I mean, this one will not be test. It's just like something I think is fine to learn. All right. So let's do the attendance thing. Pulling lunch pool. Okay. You guys can see the pool, right? Okay. And for the first problem, it's for like standard normal. Okay, I'll give you 1 more minute on submitting the pool. Yeah. Actually, I think, yeah, that's pretty, the pool should be pretty simple. I forgot the order. I should do the pool first and then ask if you are interested in this equation or not. Okay, you have 20 more seconds uh to do the pool. Actually, you have 10 seconds now. You only have 10 seconds. That's your last chance to be taken as attending the lecture, as attending the discussion. Okay, 3, 2, 1. Close pool. Okay, so like pretty much everyone answered true and true, and the answer is true and true. For the first problem, like this is like just properties of standard normal. I mean, obviously you can check using the z-score, but like it's better just to know in your head that 68 is plus minus 1 standard deviation, 95 plus minus 2 standard deviation, 99.7 is plus minus 3 standard deviation. That's something you should know in your head. And for the second problem, it's basically exactly what I wrote here. So originally I was like, I forgot the order. Like so theoretically, I should like give you the problem first and then ask you if you guys are interested in that. But like I gave it at the beginning. So yeah, and then the pool is closed. If anyone, I don't know, like I mean, I give you 3 minutes to do the poll, like and in fact you should just like do it in a minute. Oh, okay. So you want to copy the question? So basically the first problem is for normal normal distribution, for a standard normal distribution, 68 data ranking plus minus 1 SD, 95% of data lands in plus minus 2 SD, 99.7% of data lands in plus minus 3 SD. And the second problem is this here. And both of them are true. Yeah, it's fine. I will mark Alice as attending the section. You're fine. Like, don't worry about that. Yeah. I mean, if you actually attend the section and then like for some occasion you didn't do the poll, like it's a good time to ask me now before like I end the like after the discussion, like I will obviously mark you as absent. Okay, so with that being said, let's go to problem 1. So maybe I'll just like, since we don't have like too much time left, maybe I'll just like go through the problem 1 directly. So worksheet 20. Yeah. So for problem 1, we're actually employing the Chebyshev inequality to solve the problem. So we want to find for part A, we want to approximate the probability of x minus mu is greater than 2 sigma. So by Chebyshev, we know that so like Chebyshev states the probability of x minus mu that is greater than k sigma is less than k squared over 1, or it's less than equal to 1 over k squared. So in this case, k is equal to 2. So this is strictly this is less or equal to 1 over 4. So we can say that we approximate by 1 over 4 because we know that it's less than 1 over 4. And the second question, you want to approximate x minus mu that is greater than or that is less than 0.5 times mu. So again, like Chebyshev also said, the probability of x minus mu that is less or equal to k sigma is greater than greater or equal to 1 minus 1 over k squared. So in this case, we're just like saying that this is greater or equal to 1 minus 0.5 squared over 1, which is -3. But again, like we know that Chebyshev is only useful when k is greater than 1. And here is a perfect example for like exemplifying why is not useful when k is less than 1, because like when k is 0.5, we know that we are finding a probability that is strictly greater than -3. But like obviously probability are greater or equal to 0. So like it's useless. The conclusion we have here is useless. Okay, so okay, so so for problem C, we're actually calculating the exact answer. So we want to find the probability of x minus mu that is greater than 2 sigma, and we're given the lambda is 1. So what is lambda? Like we look at the back of the question, we're actually working on a Poisson random variable. So x is a Poisson random variable, which takes in a lambda of 1. So we know that for Poisson variable that the mean, which is mu, is equal to 1. Or like it is equal to lambda, which is equal to 1. And the variance is also equal to lambda, which is also 1. So the XD is the square root of lambda, which is also 1. So we're finding that the probability of x minus mu that is greater than 2 sigma, this is just sigma. So essentially we're finding that the probability of x minus 1 that is greater than 2 times 1. So that's the probability of, so we are finding that x minus mu. So we're finding that x is greater than 3 and x is less than -1. So we're finding the tails here. But like for probability of x minus -1, that's just 0, because we're talking about Poisson random variable, and Poisson random variable doesn't like take in negative values. It starts with 0. So the probability here, the first part is 0, and the second part, we know that it's just 1 minus the probability of x equal to 0, minus the probability of x equal to 1, minus the probability of x equal to 2, minus the probability of x equal to 3. Like I think there's a slightly typo on the a slightly error on part C. It should be like also minus the probability of x equal to 3. And the answer is, so remember, like for Poisson random variable, the equation for px equal to k is something like divided by k factorial times e to the negative lambda k lambda to the k power. So that's just 1 minus remember lambda is 1 here, so it's just like 1 times k, where it's 0 when x equals to 0. I don't understand what Sylvia is asking. What is the other thing? Oh no, please like clarify what you're asking. So just minus 1 to the 1, -1 factorial, and you will get the answer for part C. And then at last you will find that it is also like corresponded to it's corresponded to the upper bound we find at part A. So it will be a number, the solution will be a number that is strictly less than 0.25, because at part A we are saying that the solution is strictly bounded by 0.25. Uh, oh, okay. Yeah, we're not doing that. We're calculating the specific probability and say that the Chebyshev upper bound works for this problem. Yeah. So I guess that's why like that's the drawback of me not giving you time to read the problem by yourself. So maybe like take a minute to like scan through the solution I went through, like say if you have a problem, and maybe also like take 2 minutes to work on 2 or 3 minutes to work on problem 2. And let me know if you have any problems. And let me know if you finish problem 2. Okay. Yeah. So I mean, so for all of you, can you take a minute right now to follow the email the professor just sent to everyone here, and also copy the thing in the announcement. So maybe like, can you all of you please go to the link and check if you can log in with no problem. Because one of my students said he has a problem on logging in the web work using the external link. I just log it in and I find I have the same problem. So I just want to make sure that can everyone like follow the instruction to do the thing, to do the thing professor asked us to do. I mean, it's pretty urgent, so please do that right now. Like I also don't know about the external link. Just a student of me sent me an email saying that if you log in into through webwork.math the Berkeley.edu, if you log in through that using your email account, you will have the problem. But is it the correct way of doing the web work? Like, can anyone tell me, is this the correct way of doing web work, or the correct way is just go to the B course? Like, let me know about that.
Wait, Z, how are we supposed to log out of WebWork or just click on something in WebWork?
I mean, how do you usually log into your web work?
Usually you're like already logged in if you're on B courses. And like mine won't even let me log out, but it does say in her email to do that.
Okay, so can you explain to your classmates, like in B course, how do you do the thing? Like, do you just go to B course and then you can view midterms? Like, is it under your Berkeley credential on your B course?
Usually if you go to the lecture like course for Math 10B, there's a little tab on the side that is web work, and you click on it and it automatically logs you in and you stay on the site. Like usually you don't have to go to an external site to go to web work.
Okay, so I guess, like, because I'm not 100% sure, but like if you go through the B course and click the web work on the side tabs, that should log in you with your name and Berkeley credential. Am I understanding this correctly? So like just make sure that you can do that. And I will double check with professor if that's what she means, and I'll probably update you. I'll probably update you with whether what I mentioned is correct or not. yeah, I mean, like,
think the B courses works because when I logged in or when I click on the tab, it gives me like the practice exam. But when you try to log on to it with the website, I just get an authentication error, even though I like put in my Berkeley email.
okay. So I guess the authentication error using the website is like for everyone. So I'm not too worried about that. So I guess like you guys have just need to like go to WebWork and log in as. So if you can go to Bcourse, you should be already logged in. So I think there's no problem about that. But I will definitely check with professor and say like if there's something like I understand it's wrong or like all of us understand it's wrong. But if that's the case, I will update with you guys. All right. Thank you very much for letting me know that. I just never do the WebWork thing before, so I'm also like not too sure. But I want to make sure that everyone is on board for midterm. Like you won't like lose times or lose scores because of this logistic problem. Yeah. So with that being said, I'm sorry that I was like pretty disturbing for your problem solving process. But we have to go through the solution for problem 2. So for problem 2, you are flipping a fair coin with 100 times. So when we're talking about flipping a fair coin, that means we're talking about binomial random variables. We know that X is a binomial random variable with the probability that with probability of success of half because it's a fair coin, and we did it 100 times. So we know that the mu for the mean for binomial is NP, which is half times 100, which is 50, and the variance is NPQ, which is half times 100, 25. So the SD is equal to the square root of 25, which is 5. So like after we write down the binomial variable, we can write this information immediately. And then we look at the problem. What is the problem asking us? The problem asks us what's the probability of at least 95 heads and at least 95 tails. So that basically means for wait, can you guys see my iPad screen? Okay, I guess it's frozen again. Let me refresh it. Okay. Yeah, this is what I just wrote. So you first read the problem, you know that X is a binomial variable with this parameter, and you can find mean, variance, SD directly immediately after you know this is a binomial variable. And the question is finding X is greater than 95 or X is less than 5, because you are finding at least 95 tails means that you are finding at most 5 heads. So we want to like translate this problem into some form of X minus mean that is greater than 45. So because we want to use Chebyshev, and Chebyshev is X minus mean is greater than K sigma. So we always need to like first fix X minus mean here. So we write X minus mean and see like what are the numbers that we can fit in on the right hand side. And we know that since the sigma is 5, 45 is 9 sigma. So the question is asking us X minus 15 is greater than 9 sigma. And because of Chebyshev, this is less than K squared, which is 9 squared over 1 in this situation. Yes. And then let me go through problem 3. So problem 3 asks you that So it's basically we're given the mean is equal to 0.5 and SD is equal to 0.25. And we are asking you what's the probability of getting in 0 to 1. So like making a very accurate shot. So again, like we know that mean is 0.5. In order to use Chebyshev, we want to write it in form of x minus mu that is greater than, or in this case, it is the middle part. It's less than k sigma. So we know that mean is 0.5. So you always need to fix the mean first, write it down, and see like what are the k sigma, what are the things we need to write on the right hand side. And like obviously the 0.5 to make sure that these two are equivalent. And we know that 0.5 is 2 sigma in this case, because sigma is 0.25. Yeah. For the question Juliana asked, Ryan gave a pretty good answer. And actually, that's exactly what I mentioned here as well. So the 0.5 comes from, in order to fix the mean to be x minus 0.5, and we want this to be equivalent to the original problem, we need the right-hand side to be 0.5 to make sure that these two are the same. And we know that 0.5 is 2 sigma. So the problem becomes x minus mean less than 2 sigma. And we know that this is greater than 1 minus k squared over 1, which is 1 minus 4 over 1, which is 3 over 4. And for part B, we're basically finding the probability of x equal to 2. Like after reading the problem, you know that we are finding like not accurate shot, not in the center, and we define center to be 0 to 2. So we are finding the probability that it is out of the center. And in this time, we want to, again, because we know that mean is 0.5, mean is 0.5, we want to like fix the mean. We want to write the left-hand side of the inequality is always x minus mean. And we want to say, what can we do to make the right-hand side make sure that we are finding the actual problem. So in this case, it's x minus 0.5 is greater than 1.5. That makes sure that these two are the same. So we know 1.5 is 6 sigma because sigma is 0.25. And we know that because of the Chebyshev, this is bounded by 1 over k squared, which is 1 over 6 squared in this case. So that's all for Chebyshev. So in summary, for solving Chebyshev problem, you always need to first read the problem and identify the probability range. So you want to identify you are finding that is x a probability in between A or B, or we are finding that x is greater than A, or we are finding the probability that x is greater than A and like x greater than B and then x is less than A, like which situation it is. And after identify these three situations, we want to find, like usually we are given the mean. Usually we are given, if we are not given mean and SD, we want to find mean and SD first for specific distribution. And we want to like do some transformation on, for example, P A less than X less than B, to make it in form of probability of X minus mu that is greater than a number, whatever number it is. So you want to transform into that, and then you can apply Chebyshev. So usually you're given SD so that you know this number is how much. So you know that this is K times SD. You're given this and you have already found this number, so you know what K is. So you can apply Chebyshev and find the bond. Either it is and yeah, and also like one thing I want to highlight is that for Chebyshev, if you want to if you want to give bonds in the middle, that is always a lower bound. If you are estimating the thing in the tail, in the two tails, this is always an upper bound. Okay, so I think that's it for today. I will stay here 1 extra minute for answering problems, and yeah, if no problem, I will see you on Thursday.